Hello, this is the third video on linear transformations. And let's just review everything we've talked about linear transformations. If you have a matrix A, we get a function that sends a vector x to A times x. And that, let me make sure things are recorded. Okay. That gives you a linear transformation because it satisfies these two properties, which combined are the linearity property. And based on that, we define the linear transformation to just be any function t from Rn to Rm that satisfies this linearity property. That the sum of the inputs, if you plug in v1 plus v2, it has to go to t of v1 plus t of v2. And the second one is that if you take an input v and then scale it by c, that new input, cv, has to go to c times the original output. So that's c times t of v. And we did some examples of showing that functions are linear transformations. We gave an example of how you would prove that a function is a linear transformation, and then how to prove that a function is not a linear transformation. And okay, we saw that every linear transformation has to send a zero vector in Rn to the zero vector in Rm. And we saw another perspective of linear transformations. This linearity property can be phrased as saying that when you have a linear combination of v and w, cv plus dw, if that's your input, then the output has to be c times t of v plus d times t of w. In other words, when your input is a linear combination of v and w, then the output has to be the corresponding linear combination of t of v and t of w. And then we use that to do some practice problems, and then more generally, okay, if you just have a linear combination of k vectors, the output must be the corresponding linear combination of the k output vectors. And sometimes that's called the superposition principle. But it's really this property of linearity. All right, now let's talk about some examples of linear transformations. And that's what this video is about. So specific examples and then working with these examples. So examples of linear transformations. Well, remember that every matrix defines a linear transformation. So as soon as you write down a matrix, you already have a linear transformation. But let's take a look at some specific matrices. So let's look at this matrix cosine. So let's let theta be a real number. And let's look at this matrix cosine theta, sine theta, negative sine theta, cosine theta. Okay. Now let's think about what this matrix does. So this matrix is a 2 by 2 matrix. So the inputs are going to be vectors in R2, and then the outputs are going to be vectors in R2. So let's say that you have a vector xy, okay, which corresponds to some point here. So let's say that you have this point xy. Well, we can think about this in terms of polar coordinates. So here's r, the length. Remember, r is the distance from the origin, from the origin to this point xy. And we want to see what you get when you take this matrix and multiply that by the vector xy. Because you want to see where this matrix is going to take the point xy. And Okay, we can multiply them, but to get a better idea of what's going on, it helps to rewrite x and y in terms of polar coordinates. So remember, the first coordinate is r, the distance from the origin to xy, and then the second coordinate is the angle from the positive x-axis. So here's the positive x-axis, right? That's the positive y-axis, and then you have this angle. So let's call that angle phi, like that. Then, do you know what the coordinates of x and y are in terms of r and phi? It's r cosine phi, r sine phi. And let's just remind ourselves of why that's true. It's because when you have a hypotenuse r and an angle phi, then this length x, if you do cosine of phi, it's going to be the adjacent length over the hypotenuse. And then if you have sine of phi, it's going to be the opposite length. So this is y. It would be y over r. And then if you multiply both sides by r, you get r cosine phi is x and r sine phi is y. Okay, that's the reason why x is r cosine phi and y is r sine phi. So now let's use that. Let's use the polar coordinates. So here's our matrix, and then we multiply it by the vector r cosine phi, r sine phi. By the way, the only point that does not have polar coordinates is the origin, but the matrix is going to take the origin to the origin. So we know that the origin is going to go to itself. Okay, but the question is, what happens if you take any other point? Well, let's multiply. So we multiply that matrix by this vector. And what you're going to get is, okay, what are you going to get? Let's move it down here so I have more space. This is going to equal, so you take this first row and multiply it by the vector, you're going to get r cosine theta cosine phi minus r sine theta sine phi. That's the first component, and then the second component is going to be r sine theta cosine phi minus r cosine theta sine phi, right? And this is a vector. So this vector that we wrote, that's the output. That's where xy is going to go when you multiply this matrix by the vector xy. And now what is this vector? Well, we can use some trig identity. First of all, let's factor out the r, because I see that I can factor out the r. So on the top, I'm going to have r times parentheses cosine theta cosine phi minus sine theta sine phi, right? And then for the second component, I can also factor out an r. I'm going to get sine theta cosine phi minus cosine theta sine phi. And now, do you remember these trig identities? Cosine theta cosine phi minus sine theta sine phi, or the second one? It turns out that that's the first one's r times cosine of theta plus phi. And then the second one is r times sine of theta plus phi. So that's the output. Let's just make it clear that, so this is your input, r cosine phi, r sine phi, and when you multiply the matrix by that vector, we got this output. Now, what does that output look like on the xy plane? Well, we have the polar coordinates. Again, it's length r, and the angle that's made with the positive x-axis is no longer phi, it's theta plus phi. So originally our xy was like this, and then you had an angle phi, but then we added theta to it. So whatever theta is, okay, we added theta to it, but then we kept the distance from the origin the same. So if this is x and y, and that's theta, then this is our new output. Let's call this output x prime y prime. So this point is x prime y prime. And so what this transformation does, this matrix, is it took the point xy, our random point xy, and then moved it to x prime y prime. Well, in words, how would you describe what happened to the point xy? It rotated the point xy. It rotated this line segment theta degrees counterclockwise. So we see that this matrix, what it's doing is that it rotates the xy plane by an angle of theta counterclockwise. Okay, that's what it does. And this matrix, naturally enough, is called a rotation matrix. So for instance, if you had an example of a rotation matrix would be if you had 0, 1, negative 1, 0. Now do you see what theta will give you that? In radians, it's cosine of pi over 2. The first column is cosine pi over 2, sine of pi over 2. Second column is negative sine pi over 2, cosine pi over 2. So what this matrix does is it rotates the xy plane counterclockwise by 90 degrees. By the way, what happens if you want to go clockwise? So for instance, let's say that you have this point xy here, and you want it to go this way. Well, then you would want to subtract theta degrees, right? So you would use negative theta. So for instance, if you wanted to rotate the xy plane clockwise by 45 degrees, so that's in radians, that's pi over 4, then you would want cosine of negative pi over 4, sine of negative pi over 4, negative sine of negative pi over 4, and cosine of negative pi over 4. And the matrix, that matrix is, okay, let's review some trigonometry. So negative pi over 4 is like this. And so if you label the triangle, you get these ratios. And then cosine is going to be 1 over root 2. Sine is going to be negative 1 over root 2. Negative sine is 1 over root 2, and then cosine is 1 over root 2. So what happens is if you take this matrix and then multiply it by some vector, it's going to rotate that vector clockwise by 45 degrees. So let's do an example. Okay, I'm just going to erase this. So find the image of the point, of the point 5 comma square root of 3 after rotating the plane by 30 degrees counterclockwise. Well, why don't you take a minute and see what you get? Okay, let's see what the answer is. So what you have to do is you have to take the rotation matrix that rotates by 30 degrees counterclockwise. So that's going to be cosine of pi over 6, sine of pi over 6, negative sine of pi over 6, and cosine of pi over 6. And then multiply that by the vector 5 root 3. And that's going to equal root 3 over 2, 1/2, negative 1/2, root 3 over 2. So now you just multiply that by this vector, and if you do it out, you are going to get 2 root 3 and then 4. So it's going to go to the point. So the image of 5 root 3 is the point 2 root 3, comma 4. Okay. Now you don't only see what happens to specific points, you can actually see what happens to whole curves. So for instance, let's do another example. Describe the image of the parabola. Because remember, this transformation is taking all the points on R2. Right? It's doing something to every single point on R2. So we can think about something like the parabola y equals x squared. Describe the image of the parabola y equals x squared after rotating it by 45 degrees clockwise. So for instance, okay, let's just draw a picture. So here's the parabola y equals x squared. And you rotate it by 45 degrees. So what does that look like? So this y-axis is gonna be rotated and be like this. So then the parabola is symmetric about this new axis, and so it's gonna look like something like that. And the question is, what's the equation for this curve? Okay, that's the question. So let's just, for convenience, let's call this parabola y equals x squared c, and then we'll call the image of this parabola c prime. And we want to specify what the points on c prime are. Well, let's say, so how are we going to do that? So let's say that you have a typical point on the parabola x comma y, and let's say that it will go to the point a comma b. And you want to find some relationship between a and b. Well, we know how x and y are related, right? Because if you're a point on the parabola y equals x squared, then if you have a point xy on it, how are x and y related? Well, y is equal to x squared. That's the connection. So we somehow want to use that connection to figure out some connection between a and b. And then let's just write down what we know. We know that if you take the matrix that rotates by 45 degrees clockwise, did we figure out what that was? Yes, it's that matrix. 1 over root 2, negative 1 over root 2, 1 over root 2, 1 over root 2. If you take this matrix and then multiply it by xy, you're going to get AB. And so therefore, how can you get AB from sorry, how can you get xy from AB? If you have the point AB, what can you do to it to get xy? In terms of rotation, you would rotate by 45 degrees counterclockwise, right? To get from AB to xy. Because rotating by 45 degrees counterclockwise will, I mean, if you started with xy and then rotated by 45 degrees clockwise to get AB, then to go back, you would rotate by 45 degrees counterclockwise. So let's write the same relationship, but in terms of what you do to get from AB to xy. So now you need the matrix that rotates 45 degrees counterclockwise, and that's going to be cosine of pi over 4, so that's root 2, or let's just write it as 1 over root 2. Do I want to, let's just, actually, let's rationalize the denominator. Root 2 over 2, and then sine of pi over 4 is root 2 over 2, negative sine of pi over 4 is negative root 2 over 2, and then cosine is root 2 over 2. So if you take this matrix and multiply by AB, you're going to get xy. And let's write this out. So if you write this out, you're going to get root 2 over 2a minus root 2 over 2b equals x, and root 2 over 2a plus root 2 over 2b is equal to y, right? And now do you see why we did it like this? Because now we see that x and y are related because x squared is equal to y. Therefore, when you take this and you square it, you're going to get that. And then that's going to give you a relationship between a and b. So we know that AB is on C prime precisely when what? When you take this and then you square it, you get that. So it's when root 2 over 2a minus root 2 over 2b, when you square it, is going to give you root 2 over 2a plus root 2 over 2b. And that gives us the relationship between a and b. Now let's simplify. So we distribute the left-hand side, and we're going to get 1/2 a squared minus root 2 ab plus 1/2 b squared equals, okay, the same thing on the right. And then we can just subtract both sides. Well, we can actually multiply both sides by 2 first to make things a little easier. A squared minus 2 root 2 ab plus b squared equals root 2a plus root 2b. And just to make it a little nicer, we can get everything on one side. So a squared minus 2 root 2 ab plus b squared minus root 2a minus root 2b is 0. And that's the equation of the curve C prime. So C prime is the set of all a and b that satisfies this equation. That's the description of C prime that we were looking for. So now you see how you can use matrices to figure out what's going on. You can rotate, of course it's not just necessarily parabolas, you can rotate all sorts of things, right? Okay, I'll do a few more examples. Maybe I'll just say this very quickly. So besides rotations, there's also dilations and contractions, and that's by the matrix that's just C's on the diagonal and zeros everywhere else. So this matrix is called a dilation matrix. I mean, the terminology depends on just which book you use, but sometimes it's called a dilation matrix if C is positive, and it's called a contraction matrix if C is less than 1. And this is if C is a positive number, so. Oh, and what happens if C is equal to 1? If C is equal to 1, well, let's think about what this matrix does to xy. What are you going to get? You're going to get xy. So naturally enough, this is called the identity matrix. This is the 2 by 2 identity matrix. So why is it called a dilation matrix if C is greater than 1? So for instance, if you had 2, 0, 0, 2, what that's going to do to an arbitrary vector xy, if you multiply it, you're going to get 2x, 2y. So if you have some vector xy, let's say that's your vector xy, then when you get 2x, 2y, that just doubles the x and y coordinates. So you're going to double the length while keeping the same direction. And now just imagine doing that for every point on the plane. Right? It's going to stretch out the whole plane. I mean, what you're going to get as a result is still the xy plane, but it stretches everything by a factor of 2. And similarly, you can imagine that if you had something like a half, if your C was a half, then, so if you had something like 1 half, 0, 1 half, 1 half, 0, 0, 1 half, if you multiply it by xy, you're going to get x over 2, y over 2. That's going to be half the length. Okay? So pretty simple. And then there's also reflection matrices. So, for instance, I mean, there's lots of different reflection matrices, but for instance, let's say that you wanted one that reflected about the x-axis. So what that's going to do, what's it going to take a point xy to? It's going to take it across the x-axis, and you're going to get this point, and that's going to be x comma negative y, right? Because when you reflect about the x-axis, you're multiplying the y coordinate by negative 1. So now the question is, what matrix is going to do that? What matrix will take the vector xy to x negative y? Well, one way to think about that is you have some matrix, you're trying to figure out what these numbers are, and when you multiply it by xy, you have to get x negative y. And from that, you can see that what's going to happen is that the first row is going to be 1 and 0. Because if you did 1, 0 times xy, you're going to get x. Now, what would the second row be to get negative y? That's 0x plus negative 1y, right? So you're going to get 0, negative 1. So that matrix, this matrix reflects about the x-axis. What about if you wanted to reflect about the y-axis? So it would take the vector xy to which vector? Negative xy, right? You reflect about the y-axis, and now, of course, I'm going to ask the same question. What matrix is going to do that? What matrix will take xy to negative xy? It's going to be negative 1, 0, 0, 1. This matrix is the matrix that reflects vectors about the y-axis. or across the y-axis. Okay? And notice that whenever you have a matrix, you can say something about the columns because the matrix times 1, 0 will give you the first column. Is that something that you know? If you take a matrix times E1 is just the matrix with ones in the first entry and zeros everywhere else, you're going to get the first column of A. And similarly, if you do A times the vector EI, where EI is the vector that has a 1 in the ith entry and then zeros everywhere else, this is going to give you the ith column I of A. So for instance, in this case, the 2 by 2 case, I know that if I take this matrix, this reflection matrix, if I multiply it by 1, 0, I'm going to get 1, 0. If I multiply it by 0, 1, I'm going to get 0, negative 1. And that matches what should happen. If you take 1, 0, the result will be 1, 0. If I take 0, 1, the result will be the second column, which is 0, negative 1. Right? So if I have 0, 1, if I take this matrix, let's call this matrix A times 0, 1 is going to be the second column of A. And if I take 1, 0, then A times 1, 0 is going to be the first column of A. So in general, you can understand the matrix transformation from the matrix just by seeing what happens to these vectors E1, E2, and so on. So for instance, if I have this matrix A, which is 1, 3, 4, 5, the first column is 1, 3, and the second column is 4, 5. What does it do to the xy plane? Well, this matrix doesn't really have a pattern. Okay, it doesn't have an easy description like rotation or reflection. But the best way to describe it is it's going to take the vector 1, 0 to the vector 1, 3. And it's going to take, let me use a different color, it's going to take the vector 0, 1 to the vector 4, 5. And then we know that it's going to take the corresponding linear combination. If I have a vector AB, then it's going to go to the corresponding linear combination like, I don't know, maybe here. It will take it to A times 1, 3 plus B times 4, 5. Because my vector AB is the same as A times 1, 0 plus B times 0, 1. And where is this going to go? By the linearity, it has to go to A times the first output plus B times the second output. So it has to go to A times 1, 3 plus B times 4, 5. Okay, so this is multiplication by the matrix A. And then I usually call this transformation T sub A. Right? T sub A is this mapping from R2 to R2. That's given by the matrix A. All right, so that's some examples of linear transformations, and we'll take a look at more properties of linear transformations in the next video. Thanks.